Okay, we're going to continue reading CS3110, OCaml Programming, correct plus efficient plus beautiful. And we're on algebraic data types. So yeah, exciting. I only have a little bit to go today, so we probably will maybe finish chapter 3. Maybe we'll get further than that. We'll see what happens. I don't know how dense this part's going to be. So far, this book has been very beginner friendly, which is okay. So there's not, I guess my point in that is that there's not a whole lot of depth so far. We'll find out if that changes. 3.9 algebraic data types. Thus far, we have seen variants simply as enumerating a set of constant values, very typical of enums in other languages. So now we're going to talk about enum ADT. As a running example, here is a variant type shape that does more than just enumerate values. So we have a tuple of float that we've type aliased as point, and then you can see what happens there. Very similar to Rust. So anybody coming from Rust is going to be similar, is going to be familiar with this. But yeah, basically your enums can actually hold some values. The type shape represents a shape that is either a point. Okay, I don't need you to explain the types. The types don't matter, right? Oh, I see. No, this is the type that matters. Just kidding. This type shape represents a shape that is either a point, a circle, or a rectangle. A point is represented by a constructor point that carries some additional data, which is a value of type point. A circle is represented by a constructor circle that carries two pieces of data, one of type point and the other of type float. Those data represent the center of the circle and its radius. A rectangle is represented by a constructor rect that carries two more points. Exciting. Here are a couple functions that use the shape type. Yeah, it's fine. Like, I agree with you, Prophet. I don't love the example, but at least the explanation gets the point across of what this does. But that's okay. Here are a couple functions that use the shape type: area, function, point, circle, rect, basically pattern matching. All these different variants. Very typical OCaml code. Very typical Rust code for anybody that's used to that. Not a whole lot of surprises there. The shape variant type is the same as those we've seen before in that it is defined in terms of a collection of constructors. Okay. What's different than before is that those constructors carry additional data along with them. Every value of type shape is formed from exactly one of those constructors. Sometimes we call the constructor a tag because it tags the data it carries as being from that particular constructor. Variant types are sometimes called tagged unions. Every value of the type is from the set of values that is the union of all values from the underlying types that the constructor carries. For example, with the shape type, every value is tagged with either point or circle or rect and carries a value from. We're not going to read all that. Another name for these variant types is an algebraic data type. Algebra here refers to the fact that the variant types contain both sum and product types, as defined in the previous lecture. The sum types come from the fact that a value of a variant is formed by one of the constructors. The product types come from the fact that a constructor can carry tuples or records, whose values have a sub-value from each of their component types. Okay, let me see if I understand what he just said. Okay, yep, we're good. We've got product types and sum types together. And once we put those together, we call them ADTs. Using variants, we can express a type that represents the union of several other types, but in a type-safe way. Here, for example, is a type that represents either a string or an int. Technically speaking, that's not entirely true since variant constructors that take multiple parameters and tuples are slightly different. Yeah. Okay. I feel you. But that wouldn't be represented the same way, right, Prophet? Like, it would look different. Like saying rect of point star point, that is still a rect of tuple, point and point, right? Or is that not true? That is a rect with two parameters. Oh, okay. Yeah, I didn't know that. I just assumed it was a tuple. Because you cannot do let x equals 1 to in rect x. Oh, interesting. Yes, that makes sense. So it is actually its own type. It is not the same thing as a tuple. OCaml pretends really hard that it's a tuple. That's hilarious. Okay. Good to know. Constructor can carry tuples or records. Yeah. So he's just kind of simplifying by saying tuple, maybe. Yeah, right. Right. If you put the parens around them. Because then it constructs it as a tuple itself. Uh-huh. Yeah. That makes sense. Okay. If we wanted to, we could use this type to code up lists, e.g. that contain either strings or ints. Okay, I missed it. I missed his explanation above. I think I skipped a paragraph. Yeah, here we go. Using variants, we can express a type that represents the union of several other types, but in a type-safe way. Here, for example, is a type that represents either a string or an int. Type string or int, string of string, int of int. Nice. Okay. If we wanted to, we could use this type to code up lists that contain either strings or ints. Needs more parens, right, Nunez? That's what Lispers think. You just add some parens, you got a Lisp. I found a Lisp that I didn't know about, which, I mean, there's so many Lisps, so it's not like that's too surprising. But I thought it was kind of cool. I put it in my Lisp channel in the Discord. Little Fennel. What a cute little name, a little mascot. Essentially Lua interrupt Lisp. It's nice. I figured you'd know about Fennel Rond. It does seem pretty nice. The part that I thought was really cool, I mean, of course, like just being able to write this, easily call any Lua function or library from Fennel and vice versa. So complete interop between the two. I think that's really cool. But that you can ship compiled code with no runtime dependency on Fennel. So basically, Lua is a compile target of Fennel, you could say, right? And embeddable, yeah, that Fennel is a one file library as well as an executable. So you can also put Lua in, put Fennel in like a Lua program or whatever, and then you have all of the cool Lisp stuff, but in your Lua application, if you will. That's the way I read those points. So I thought that was pretty cool. Fenneling. It's neat. You always end up using something, Ron, that makes you use another language. Okay. Is this where we are? Yeah. Okay, so he's going on with his string or int list example. Yeah, there you go. Using variants in order to have, you know, multiple underlying types. I don't know how you want to say that in a list. Variants thus provide a type-safe way of doing something that might before have seemed impossible. You always end up with some form of Lisp. It's everywhere, buddy. Everything eventually reduces down to a Lisp. Even OCaml, it reduces down to S expressions at the end of the day. Maybe not a Lisp exactly, but pretty close to it. At least as at one pass of the compiler. Variants also make it possible to discriminate which tag a value is constructed with, even if multiple constructors carry the same type. Okay, for example, type T equals left event, right event. Yup. Left one. So basically, he's showing us an either without calling it an either. Got it. And then syntax and semantics. What was really fun is back in the day when I wrote the language that shall not be named, is I did an either implementation, my own, of course, rolled my own either implementation. And it was ugly, as you can imagine. Anything that you write in that language that's relatively functional is. To define a variant type T equals C1 of T1, Cn of Tn. Okay. The square brackets above denote that of T is optional. Oh, I see. This is the syntax things he goes through. Yeah, I don't need to read this. This is fine. I just don't like it. And always do church encodings. Yeah. I'll pass. And we extend the definition of when a pattern matches. Okay. Catch-all cases. One thing to be aware of when pattern matching against variants is what real-world OCaml calls. Oh, he's calling out the other main OCaml book that people read. He is calling them out right now. Let's see. Let's see the OCaml drama. Here's a simple example of what can go wrong. Let's suppose you write this variant in function. Type color equals blue or red. 1,000 lines of code in between. Let string of color function blue underscore catch-all red. Okay, seems fine, right? But then one day you realize there are more colors in the world. Okay, so we pretty much know where he's going with this. I don't really get the I guess he's just calling out real world OCaml just to say that he's stealing what they call them. Catch-all cases. Okay. I mean, why not just call it? I mean, that's fine, but it's just kind of a weird thing. It threw me for a loop. I was hoping for some like drama here. Yeah. Right? I know. But like I thought he was going to be like, and they do it in this way that's wrong. But no. Sadly no. It's just he's just basically what's that called? I haven't been in school for too long. What's the thing? A reference? Yeah. Way too nice. The problem is the catch-all case in the pattern match inside string of color. The final case that uses the wildcard pattern to match anything. Yes, yes. Instead, you should just be exhaustive in your variants unless you have a really good effing reason not to, okay? Yeah. Catch-all cases lead to buggy code. Avoid using them. Somewhat agree. Somewhat agree. Okay, recursive variants. Variant types may mention their own name inside their own body. For example, here is a variant type that could be used to represent something similar to int list. Okay, type int list is nil or cons of int star int list. Okay. Right. And this is how we often will represent things like trees and linked lists even, and all those kinds of things, right? Which is basically defining a linked list right here. It's just his own special linked list that only allows integers. Okay. Let list 3, cons 3 nil, cons 1, cons 2, list 3. Yep. Let rec sum, sure. Look at that. Notice that the definition of int list, we define the cons constructor to carry a value that contains an int list. This makes the type int list be recursive. It is defined in terms of itself. Types may be mutually recursive if you use the and keyword. Nice. Type node equals value int, next my list, and my list equals nil or node of node. Neat. Any such mutual recursion must involve at least one variant or record type that the recursion goes through. For example, the following is not allowed. Okay. Okay, yeah, that makes sense. The definition of T contains a cycle U. I guess that's not the worst OCaml error I've ever seen. It kind of makes sense what they're saying. But this is type T U of U and U equals T of T. Very helpful type. Record types may also be recursive. I mean, actually, I guess that could be an OK type. It is, I don't know what you would use that for, but that's okay. Not for me to think about. Prophet already knows. Record types may also be recursive. Yes, type node equals value int next node. Cool. But plain old type synonyms may not be. Is this really the right thing that OCaml calls these? Type synonyms? Is that what they're actually referred to in OCaml? Type synonym OCaml. Seems like it. Okay, this is a synonym alias. Okay. For variables used as aliases when the type they are aliased to would be invalid in the scope of the enclosing definite. Okay, so here, I mean, it makes sense to use the word alias in this sentence. So I'm going to go with that they don't have aliased and recursive types. Okay, well, in the OCaml manual, they seem to prefer the term alias. Now, whether that's actually like a community thing or not, I typically will call them aliases, so that's fine. I guess sometimes I call them new types, which I know is probably even more ambiguous. Yeah, it doesn't seem like they're super consistent, because new types are technically not that. Why do I call them new types? New types is like something else, isn't it? So am I misspeaking when I call them new types? New type. I know what it is in Haskell, like exactly. Okay. Isn't this just like a single variant? They're sort of like new types if you don't expose the... Yeah. I'm just wondering where my brain picked that up. because that's what I call them in Rust. I usually say that I'm new typing something. But really, like, I think type aliasing is probably the more accurate one. Search for type abbreviation. Oh no, is this another one of is this okay? Nice. Record types type abbreviation. Okay. This defines the type constructor as an abbreviation for the type expression. Oh, interesting. Okay, type abbreviation. Let's go. So we don't call them aliases or synonyms here. We call them abbreviations. Okay. Interesting. I mean, type abbreviation is not the worst name, I guess, but sometimes it's not actually abbreviating. Officially. So officially it's abbreviation. I hate that. I'm gonna keep using the word alias probably. No, that's a good call out though, because now I know what if people use type abbreviation, that's what they mean, whether or not it's actually shorter. Record types may also be recursive, but plain old type synonyms may not be. Alias is shorter than abbreviation. Nice. We just have to type alias equals abbreviation, right? And then we're good. Boom. Fixed it. Okay. Type node equals value int next node. Type node equals value int next node. Yeah, but plain old type synonyms may not be. Okay. Type T equals T star T. Although node is a legal type definition, there's no way to construct a value of that type because of the circularity involved. Yeah. That's really funny. This is like only representing the cons case in a linked list. It's great. Parameterized variants. Variant types may be parameterized on other types. For example, the int list type above could be generalized to provide lists coded up ourselves over any type. Type a my list equals nil, cons of a star a my list. Okay. Right? Yes. We have now made a linked list that's generic. Nice. I don't think this is going to have a whole lot of interesting information for me. Fun fact, if you turn on rec types, that type T equals T star T example compiles. Oh no. So basically you can compile things that are impossible to actually construct. Nice. So yeah, you can have generics in your type definitions. Who knew? Who effing knew? All right. Let rec length equals function, nil cons. Yep. Parametric polymorphism, generics, same thing. Let rec equal, let rec x equals x x. Oh dear. Now you're just hurting me, Prophet. Yes, we know all about polymorphism because we're functional programmers. That's like a cyclical doubly linked list, sort of. Yeah. It's bad. It's actually just bad. We can just call it bad. It is also possible without any elements. It is also possible to have multiple type parameters for a parameterized type, in which case parentheses are needed. Okay, let me think about this. Type A, B pair equals first A, second B. Did I miss something? I might have skipped over it just because it's like, yeah, generic's not interesting, but I don't know if this syntax is like 100% in my head. So very similar to Rust in that you were, of course, specifying your generic type parameter on the left-hand side. Okay. Got it. I think that's the only thing. And you have to use parentheses if you have more than one. Okay. Check. Good. Understood. Polymorphic variants. Well, yeah, I know. I knew you were going to say that. Yes, you would. I think I still think of it as on the left-hand side. Like it's the type definition. But oh, you know what I was thinking of actually? What I was actually thinking of is lifetime annotations. Hilarious, classic. Since they look the exact effing same. I think that is probably one of the most interesting design choices of Rust, is that, like, you know, the guy who created it, of course, like, knows OCaml, wrote the first compiler in OCaml. I think most people who are here know that. But like, I think it's just funny that he used the OCaml generic syntax for his lifetime syntax. I don't know if this was him or not. But then, like, there's so many things that still seem kind of like this, like specifying lifetimes. I think on the left-hand side, right? I'm not crazy when I'm thinking about that. I mean, I guess maybe it's still on the right-hand side. I don't know. I have a hard time sometimes picturing things abstractly in my head. But yeah, it's just interesting to me. So there's a lot of similarities between the syntax of lifetimes and OCaml generics. And I just think that's weird that that was the choice. But it's not like I have like a great example of what should have been done instead. But you know, whatever. Thus far, whenever you've wanted to define a variant type, you have had to give it a name such as dayshape or alpha my list. Occasionally, you might need a variant type only for the return value of a single function. For example, here's a function f that can either return an int or infinity. You are forced to define a variant type to represent that result. Okay, yes. The downside of this definition is that you're forced to define fen or env even though it won't be used throughout much of your program. There's another kind of variant in OCaml that supports this kind of programming. Polymorphic variants. Polymorphic variants are just like variants, except you don't have to declare their type or constructors before using them. Okay, I actually have never used this at all in OCaml. So this is new. This is all new to me. This is the first thing that's like really new to me. Polymorphic variants. I've heard people talk about them. I've never actually used the syntax. You don't have to declare their type or constructors before using them. There is no name for a polymorphic variant type. So another name for this feature could have been anonymous variants. Sure. The constructors of a polymorphic variant start with a back quote character. Using polymorphic variants, we can write f, let f equals function 0, 1, in. Okay. This type says that f either returns a finite n for some n int or infinity. The square brackets do not denote a list, but rather a set of possible constructors. Oh, yeah. Okay, that they're saying in the type signature. Oh, wow. I want to see this. Get to the right browser. See if it opens in the right one. Type pair t equals to tt. Oh, interesting. They used parens there. I guess, is it Scala that uses these straight braces? I've never written Scala. It's been a long time since I've read Scala. I would love this. I hate typing arrows. And I guess part of the reason I like it is because I like using fewer characters and like necessary syntax. Uses _1 and _2, etc. for tuple access. Interesting. You prefer pair t, comma t, tbh? Yeah. Type syntax shouldn't be different than term syntax for no reason. Yeah. I mostly would agree with that. But I prefer this over arrows. That's all I'm going to say. But I think you hit the nail on the head. It was probably Yawar. I think they just basically just tried to make it look more and more like C and C++, right? Because that way people don't get scared away by syntax. They just get scared away by everything else in Rust instead. Okay, polymorphic variants, right? So basically, instead of defining our own variant, people still complain about Rust syntax. It's so true. It's so true. I mean, I don't necessarily love Rust syntax myself, but I like the language in general. Por lo general. Okay, got it. So this just basically allows us to not have to define a type if we're not going to really use that type other places. We can just do this. It's perfectly fine for the pattern match to include constructors other than finite or infinity because f is guaranteed never to return any constructors other than those. Okay. There are other more compelling uses for polymorphic variants that we'll see later in the course. They are particularly useful in libraries. For now, we will generally steer you away from extensive use of polymorphic variants because their types can become difficult to manage. I guess my other question, I guess they'd be scoped by module. Like, how are polymorphic variants scoped? Is it scoped by module? The way everything else is? They're not, like, as in, if I wrote something, they're row polymorphic. Okay. So then in that case, it would be valid for me to return a finite int in one place and a finite something else in another place, but technically they're not the same type. I mean, technically and realistically, they're not the same type. If I just really wanted to screw people over. Yeah. I guess that makes sense because then a finite event anywhere else is just, so a finite event anywhere in the program, if you will, would be the same. Hey Dylan, what's up? Thanks for joining. You want me to stand up, don't you, Rond? Okay, I'm standing up right now. I'm not going to read chat. I'm just standing up. I'm just kidding. All right, fine. We'll go to short metamy. The short version. Hey, Sabine. How's it going? Okay, so we were just talking about polymorphic variants, and that was interesting. I've actually never used polymorphic variants before, so that was new to me. I've heard people talk about them. I probably watched Dylan use them, but it's not like I pay super close attention to Dylan, so there's that. Okay, built-in variants. OCaml's built-in list data type is really a recursive parameterized variant. You're using them pretty extensively in Dream HTML. Oh, that's cool. I should read that code just for funs. Yeah, it does. It basically it basically shows them and then says don't use them. But at least it shows them. You don't pay attention to what I do either. That's what I was laughing about. That's funny. It's good. OCaml's built-in list data type is really a recursive parameterized variant. It is defined as follows: type alpha list equals nil or cons of a star. I said alpha the first time and then I said a the second time. Dang it. Cons of alpha star alpha list. So list is really just a type constructor with value constructors nil, which we pronounce nil, and cons, which we pronounce cons. Boom, got him. OCaml's built-in option data type is really a parameterized variant. It's defined as follows: option, none, or sum of alpha. Yep. Option is really just a type constructor with value constructors none and sum. Yeah. All great examples. Takes some of the mystery out of things. Exceptions. OCaml has an exception mechanism similar to many other programming languages. A new type of OCaml exception is defined with this syntax: exception E of T. Got it? Where E is a constructor name and T is a type, the of T is optional. Notice how this is similar to defining a constructor of a variant type. Yes. To create an exception value, use the same syntax you would for creating a variant value. Here, for example, is an exception value whose constructor is failure. lot of failure around. There was a joke, I couldn't quite form it, which carries a string. Failure, something went wrong. This constructor is predefined in the standard library and is one of the more common exceptions that OCaml programmers use. Yep. To raise an exception value E, simply write raise E. There's a convenient function, fail with string to alpha in the standard library that raises failure. That is fail with S is equivalent to raise failure S. Okay, cool. I've seen that. To catch an exception, use the syntax, try E with P1E1, PNEN. The expression E is what might raise an exception. If it does not, the entire try expression evaluates to whatever E does. If E does raise an exception value V, that value V is matched against the provided patterns, exactly like match expression. Exceptions are extensible variants. Nice. Okay, this is I had this question when I was reading it. It's like, how is this defined as an actual variant? All exceptions values have type EXN, which is a variant defined in the core. It's an unusual kind of variant, though, called an extensible variant, which allows new constructors of the variant to be defined after the variant type itself is defined. See the OCaml manual for more information about extensible variants if you're interested. Oh, really? Okay, cool. He's using an extensible variant for riot messages. That makes sense. So that they still all have the same type, but then you can create new variants. So glad I said that out loud. 3.10.2, exception semantics. Since they are just variants, the syntax and semantics of exceptions is already covered by the syntax and semantics of variants, with one exception, pun intended, which is the dynamic semantics of how exceptions are raised and handled. Nice. Exception, exception. Classic. Yeah, that makes sense. I'm not going to read dynamic semantics because I don't like to, and I'm going to say that every single time I get to the semantics section of this book. It just bothers me for some reason. And it's fine, just not for me. We're not reading the semantic sections. This one does seem like there's a lot of interesting information. I guess I'm going to break my own bias right now. What did he go over? Usually they're just like boring and they don't tell me anything I don't already know. Okay. Yeah, this is a really long section. Okay, I guess we're just going to read this whole thing. As we originally said, every OCaml expression either evaluates to a value, raises an exception, or fails to terminate in an infinite loop. So far, we've only represented the part of the dynamic semantics that handles the first of those three cases. What happens when we add exceptions? Now, evaluation of an expression either produces a value or produces an exception packet. Packets are not normal OCaml values, damn it. The only pieces of the language that recognizes them are raise and try. The exception value produced by e.g. failure oops is part of the exception packet produced by raise failure oops. But the packet contains more than just the exception value. There can also be a stack trace, for example. Okay. For any expression E other than try, so basically the packet is like it's like the exception context in Java is what we call it. Or maybe we just call it that way in Clojure, but we can do that for Java exceptions too. I don't know what Java actually calls them. For any expression E other than try, if evaluation of a subexpression of E produces an exception packet P, then evaluation of E produces packet P. This is when I stop liking these examples. Okay. Sure. But now we run into the problem for the first time. What order are sub-expressions evaluated in? Sometimes the answer to that question is provided by the semantics we have already developed. i.e. exceptions are passed. Oh, right. Okay. Oh, yeah. I read the first E. I read expression as exception in that sentence, and I was quite confused. Okay. Nice. Good. I read it that way in my head anyway. Yeah. We're good. Clearly. That's how exceptions work. But now we run into a problem for the first time. What order are sub-expressions evaluated in? Sometimes the answer to that question is provided by the semantics we have already developed. For example, with let expressions, we know that the binding expression must be evaluated before the body expression. So the following code raises A. Let underscore equals raise A and raise B. Okay. Exception A. And with functions, OCaml does not officially specify the evaluation order of a function and its argument. Yeah. but the current implementation evaluates the argument before the function. So the following code also raises A, in addition to producing some compiler warnings that the first expression will never actually be applied. Classic not specifying the evaluation order of functions and arguments. It makes sense that both those pieces of code would raise the same exception, given that we know, okay, I don't care. But what does the following code raise as an exception? Raise A, raise B. Okay, this is the part that piqued my curiosity, is when he said, the answer is nuanced. The language specification does not stipulate what order the components of pairs should be evaluated in, nor did our semantics exactly determine the order, though you would be forgiven if you thought it was left to right. So programmers actually cannot rely on that order. The current implementation of OCaml, as it turns out, evaluates right to left. So the code above actually raises B. If you really want to force the evaluation order, you need to use let expressions. Okay. Exciting. That code is guaranteed to raise A rather than B. One interesting corner case is what happens when a raise expression itself has a sub-expression that raises. It's just funny, like how deep he's going into these dynamic semantics, and all of his other ones are just like da-da-da-da-da on like more important things, but exceptions, he's going for it. He really likes how the exceptions work. No, I mean, this is all really cool information. It's just interesting. One interesting corner case is what happens when a raise expression itself has a sub-expression that raises. Exception C of string, exception D of string. Raise C, raise D. Oops. Nice. That code ends up raising D because the first thing that has to happen is to evaluate C, raise D, oops, to a value. Yeah, that's what I would expect. I'm not going to read all those words. Yeah, I don't think it's that interesting. Did he say it was interesting? Interesting corner case. I mean, is that interesting? Oh, Prophet, you're so funny. You make me laugh. Yeah, I don't know anyone that would look at this code and be like, I bet C is going to raise first. Good times. Once evaluation of an expression produces an exception packet P, that packet propagates until it reaches a try expression. Yeah. In other words, it bubbles up the call stack. How about that? The exception value inside P is matched against the provided patterns using the usual evaluation rules for pattern matching, with one exception. Man, this guy can't stop himself. If none of the patterns match, if none of the patterns matches, wow, wrong English. I've never made an English mistake. Then instead of producing match failure inside a new exception packet, the original exception packet P continues propagating until the next try expression is reached. Oh, right. Yeah. Okay. Typical try catch behavior. If you don't match on the exception that is being raised at that time, like in your try, then it just goes up to the other one. Yeah. Yeah, exciting. Wow, this is a long one. Or maybe there's just a lot of words. 1 second. Okay. Pattern matching on exceptions, I guess. There is a pattern form for exception. Here's an example of its usage. Match list.hd nil with nil empty. Cons non-empty. exception failure S. Okay. Note that the code above is just a standard match expression. Hey, Mad Flash. We can do that in just a second. Not a try expression. It matches the value of list.hd against the 3 provided patterns. As we know, list.hd will raise an exception containing the value failure hd. The exception pattern, exception failure S, matches that value, so the above code will evaluate to hd. You accidentally clicked. I can refund your points if you want, or we can do it. That's funny. Well, welcome anyway. In general, exception patterns are a kind of syntactic sugar. Consider this code. Match E with P1. Yeah, okay, it's the normal match syntax code. He got first, guys. Come on. Hour and 10 minutes in, and he got first. Unbelievable. Or they, you know. Not accidental, that one. You did it. Let most American thing I've ever said. Oh, there's so many good levels, Rond. That was good. That was good. Clap for Rond. Then we can rewrite the code as try match E with R1 E1 RN EN with Q1 E1 QM EM. Okay. Which is to say, try evaluating E. If it produces an exception packet, use the exception. I don't understand the point of this. Hey. You should be good. Just don't go in front of the TV. Having a losing battle with a borrow checker. You're working with Rust. Okay, I don't exactly. Okay. If it doesn't produce an exception packet, but instead produces a non-exception value, use the non-exception patterns from the original match expression to match that value. Try match E with. Oh, okay. Why would you write this code? I'm not getting it, but that's fine. I don't care that much. Exception to no unit. If it is part of a function specification that it raises an exception, you might want to write OUnit tests to check whether the function correctly does so. Here's how to do that. Boom. You'd write that before OCaml introduced the exception pattern syntax sugar. Oh, okay. Okay. I understand now. Okay. That part wasn't clear to me. Thanks, Yahweh. Coming in clutch, as usual. So if it's part of a function spec that it raises an exception, you might want to write OUnit tests that check whether the function correctly does so. Exception patterns are pretty nice, actually, because your catch is only scoped over the scrutiny of the match, so you don't actually accidentally catch too many exceptions. Okay. That makes sense. You might want to write OUnit test to check whether the function correctly does so. I read that like 10 times now. Here's how to do that. Assert raises. Assert raises is your friend. If you want to test that your function is actually, that's if you're using OUnit. Does anybody use OUnit? Doesn't everybody use other things like, what is it, Alco test? I don't know. The expression assert raises exc fun parens E, checks to see whether expression E raises exception X. So if so, the O unit test case. Okay, he's just explaining what this test does. I think it's pretty obvious what the test does. Oh, I didn't know this. Okay. Then he goes and says something interesting. Note that the second argument of assert raises is a function of type unit to alpha, sometimes called a thunk. Is that really what a thunk is? It may seem strange to write a function with this type. The only possible input is unit. But this is a common pattern in functional languages to suspend or delay the evaluation of a program. Yeah, that's what I did. That's what I thought. Yeah, thunk is something else. Yeah. Like isn't a thunk like in Haskell, since things are lazy, everything is like a thunk. Like the lazy operations anyway, whatever, are in a thunk. And then when you call that thunk the first time, it caches the result. And that way, every time you call it after that, the result is already cached, etc., etc. That might have been a bad way of putting it, but yeah. There we go. Look at me. OCaml has that with lazy T. Okay. Classic lazy T. Unbelievable. In this case, we want assert raises to evaluate list.hd when it is ready. If we evaluated list.hd immediately, assert raises would not be able to check if the right exception is raised. We'll learn more about thunks in a later chapter. Will he be correct, though, in a later chapter? That's what we don't know. A common error is to forget the fun around E. If you make this mistake, the program may still type check, but the O unit test case will fail without the extra anonymous function. The exception is raised before assert raises ever gets a chance to handle it. Okay, sure. Okay, example trees. Not surprised that we're going to go over this now. Got 25 minutes left. We might actually finish chapter 3. Of course, then I'll be going. Then next time I have to do exercises without remembering anything that we just went over. But at least most of this isn't new. It'll test whether I actually retained information, I guess. Trees are a very useful data structure. A binary tree, as you recall from CS3110, does everybody recall it from CS2110? Is a node containing a value and two children that are trees. A binary tree can also be an empty tree, which we also use to represent the absence of a child node. Here's a definition for a binary tree data type. Type alpha tree equals leaf or node of alpha star alpha tree star alpha tree. Yep. A node carries a data item of type alpha and has a left and right subtree. A leaf is empty. Compare this definition to the definition of a list and notice how similar their structure is. So effing similar. The only essential difference is that cons carries one sublist, whereas node carries two subtrees. Here's a code that constructs a small tree. Yes. You are correct. You are correct in that it constructs a small tree. The size of a tree is the number of nodes in it. That is nodes, not leaves. Leafs. For example, the size of tree T above is 7. Here's a function that returns the number of nodes in a tree. Yep. It's funny that, I mean, I guess he's just going for brevity, but like, of course, that doesn't like take advantage of TCO, right? Kind of interesting. It's fine. Representation with records. Next, let's revise our tree type to use a record type to represent a tree node. In OCaml, we have to define 2 mutually recursive types, one to represent a tree node and one to represent a possibly empty tree. Okay, yep. This is actually how I typically... You can't make that take advantage of TCO without CPS, actually, because your recursion isn't linear. Oh, you're right. Yeah, that makes sense. Since you have to go multiple places. Got it. That makes sense. Yeah, exactly. In OCaml, we have to define 2 mutually recursive types, one to represent a tree node and one to represent a possibly empty tree. Okay. Yep. This is more like how I have a binary tree in Rust. Wait, what? Have is a bit strong here. I forget. I don't know, but yeah. We can use pattern matching to write the usual algorithms for recursively traversing trees. For example, here, example. That's how you're actually supposed. If you're not a non-native, I mean, no. If you are a non-native English speaker, just so you know, that's how you are supposed to say that word. It's example. Oh, right. Yeah. Like you don't have to, but you can write your tree like a normal person. Yeah. For example, here's a recursive search over the tree. Yeah. Write that down, Ron. Make sure you do it. Let rec mem x equals function leaf false node blah blah blah. Yeah. Looks good. The function name mem is short for member. Is it though? Studlib often uses a function of this name to implement a search through a collection data structure to determine whether some element is a member of that collection. Here's a function that computes the pre-order traversal of a tree in which each node is visited before any of its children by constructing a list in which the values occur in the order in which they would be visited. Okay. Let rec pre-order equals function leaf node value left right value at pre-order left at pre-order right. Oh yeah, because that is just list concat, right? Okay. Yep, that makes sense. Although the algorithm is beautifully clear from the code above, it takes quadratic time on unbalanced trees because of the at operator. That problem can be solved by introducing an extra argument ACK. Okay, so now he's explaining that we could make this better using an accelerator. Preorder len t preac ACK equals function leaf ACK. Node value left right. Value cons pre-ack, ack right, and cut off. Just completely cut off. Okay. Pre-ack, ack right. Yeah, pre-ack left. Okay, sure. Or you could, not use singly linked lists for everything. As in, you should use a doubly linked list, right? Is that your point? Your point. I mean, your point is to use a doubly linked list, right? The version above uses exactly one cons operation per node in the tree, making it linear time. Boom, linear time. Oh God. Okay. Concatenation on mutable doubly linked lists is constant. Oh yeah. Okay. Fair. That would actually be nice. The version above uses exactly one cons operation per node in the tree, making it linear time. Boom. 1. Okay. We can define a recursive variant that acts like numbers, demonstrating that we don't really have to have numbers built into OCaml. For sake of efficiency, though, it's a good thing they are. Why? Why not just do 0 and suck? Just like we do in Agda. A natural number is either 0 or the successor of some other natural number. This is how you might define the natural numbers in a mathematical logic course. And it leads naturally to the following OCaml type, nat. We have defined a new type nat, and 0 and suck are constructors for values of this type. This allows us to build expressions that have an arbitrary number of nested suck constructors. Such values act like natural numbers. Okay. Okay. Explaining how to use. This is all you need. If you read this, you'll be ahead of the game when you use theorem prover languages. To determine whether a natural number is even or odd, we can write a pair of mutually recursive functions. Algebraic even equals function 0 true, suck m odd m, and odd equals function 0 false, suck m even m. Yep. Very nice. Summary. Lists are a highly useful built-in data structure in OCaml. The language provides a lightweight syntax for building them rather than requiring you to use a library. Wow. This is already too much reading for me. Accessing parts of a list make use of pattern matching, a very powerful feature, as you might expect from its rather lengthy semantics. We'll see more uses for pattern matching as the course proceeds. This built-in lists are implemented as singly linked lists. That's important to keep in mind when your needs go beyond small to medium-sized lists. Recursive functions are on long lists will take up a lot of stack space, so tail recursion becomes important. Okay, good callouts. Don't use linked lists if you need something like an array or something like that. OCaml provides data types for variants, tuples, and products, and options. Pattern matching can be used to access values of each of those data types, and pattern matching can be used in let expressions and functions. Association lists combine lists and tuples to create a lightweight implementation of dictionaries. Variants are a powerful language feature. They are the workhorse of representing data in a functional language. OCaml variants actually combine several theoretically independent language features into one. Some types, product types, recursive types, and parameterized polymorphic types. The result is an ability to express many kinds of data, including lists, options, trees, and even exceptions. Very cool. So then we just have some exercises. Let's see how we do. Still have a little bit of time. List expressions. Construct a list that has the integers 1 through 5 in it. Use the square bracket notation for lists. Okay, this is going to be hard. This is going to be really hard, guys. Let's see if I can do it. Did it. Okay, construct the same list, but do not use the square bracket notation. Instead, use cons and nil. Okay. Let's see. Can I do it? Beautiful. Construct the same list again. This time the following expression must appear in your answer. 2, 3, 4. Use the add operator and do not use cons. Yeah, I did okay. I did okay. I really thought about it. Okay, so then I guess they want me to do this. 2, 3, 4, and 5. Whoops. Yay. So good at school. Write a function product that returns the product of all the elements in a list. The product of all the elements of an empty list is 1. That returns the product of all the elements in a list. The product of all the elements of an empty list is 1. Okay, let's just go into an actual buffer because I'll be annoyed to write this out. Let product equals function. What did he say? It's 1. The product of all the elements of an empty list is 1. Yeah, okay. Classic 1 base case for multiplication, right? And then, well, it might help if I did this right. Okay. Should we be better about this? Do like head tail. And then we just say H star product tail. You think that's right? Product. I actually don't know what the product is of this. It's probably that though, right? Yep. How about it? So good. Write a function that concatenates all the strings in a list. The concatenation of all the strings in an empty list is the empty string this. I don't think that's very interesting. I guess I'll just write it for fun, for the heck of it. Concat equals function. Oh, what did it say? I forgot what the base case was. Concatenation of all the strings in an empty list is the empty string. Reasonable. Weird that didn't work this time. Nope. H tail. H star. No, caret, I mean. Caret. Come on. Come on, computer. What are you doing? Emacs? Oh. Args out of a range 70. Haven't seen that one in a while. It's all right. We just have to start over in a new frame. It's all good. I hit 70. That's reasonable. H caret concat tail. Okay. I'm not. I guess we should just test these to make sure I don't do anything dumb. Hey, you guys. Hey guys. Using pattern matching, write 3 functions, one for each of the following properties. Your function should return true if the input list has the property and false otherwise. The list's first element is a big red. Okay. Nice. This is obviously supposed to be called big red head. And big red head equals function big red that's what I meant. True. Oh my gosh, false. It is the list's first element. Okay, just making sure. Big red head. Big red head. Yeah, I did. I sure did mean that. Thanks. So good at this. All right. The list has exactly 2 or 4 elements. Do not use the length function. Okay. 2 or 4 function. True. Well, that didn't work. Well, if I knew where keys were on my keyboard. False. Let's go. I'm sure there is. You can tell me. You can tell me if you want. Did I just forget something? Let's see. What's an easier way to match on the fact that something has 2 or 4 elements? And closing my eyes for a second. Is it in my head? I don't think it is. Oh, you mean, just using a list literal syntax. Yeah, that is a little bit simpler. Instead of using the con syntax. Yeah. That's fair. But this makes you feel like you're in Lisp land and happy, right? Just kidding. The first 2 elements of the list are equal. Okay, using pattern matching. That's a really dumb thing to write using pattern matching. I don't like that. You can use an OR pattern. Oh, right. I don't remember him going over that, but maybe I just skipped over it because I'm me. Exercise library. Consult the list standard library to solve these exercises. And it's 3:24, so I should probably wrap up because I actually have a hard stop at 3:30. We'll get back to it though. We'll finish up these exercises next time. Let's see how much we have left. We still have quite a bit. Higher order programming. Yeah, this is going to take me a lot longer than I thought it was going to. Classic. But that's cool. It's been fun. It's been fun to go through either way. I gotta stop here and find somebody to raid.